I'll show you examples, but I also want to familiarize you with using this binomial distribution table. Okay, so we'll start by looking at that. So your binomial distribution table has 4 pages. 1, 2, 3, and 4. And those little n's, how many possible outcomes there are in our sample space, are going to be along the side. So our little n is at the top. All right, and we're going to see that our table goes from only taking 1 sample, that's really boring, 2, 3, 4, etc. 8, 9, 10, 11, 12, 13, 14, and then it skips to 15 and to 20. And each of these little n's along the left-hand side is accompanied by a list. We'll zoom in on point 5 here. Right, each of our little n's is accompanied by a list of, if we're taking a sample of 5, how many possible outcomes are there? Well, out of our sample of 5, we could have 0 successes, 1 success, 2, 3, 4, or 5 successes out of our 5 ships. Okay, so if we are going to sketch a probability distribution based on our binomial distribution table, then these are the values of x we're going to put across the x-axis. And then each of these probabilities is the probability we're going to draw for that x value on the y-axis. So when we were looking at this formula a few minutes ago, and we said all you need to know is the little p and the n, then you have to sequentially calculate all the values of the probabilities for each of the possible values of x. Right, here is our table that's showing us what those are. Right, so somebody's already made those calculations for you. Thank goodness. All right, now why are there multiple rows or sort of columns across the table? That's because we might be interested in different values for little p. All right, so little p, we have to have these 2 things. We have to have little n and we have to have little p. We have a little p of 0.5. Then we're going to go to this set of values. And so each of these sets of values is for one combination of little p and little n. All right. So when we looked at probabilities early in the semester, we looked at how many children, if we get children that are half boys and half girls. So if our probability is 0.5 of getting a boy for every child that we have, and we have 3 total children, what is our probability of getting 0 boys, of getting 1 boy, of 2 boys, of 3 boys? All right, so if that was our question, then all we have to do is read it off the table. Right, so if you were asked the question, what is the distribution of number of boys in a family of 3 children? And what are the possible outcomes of number of boys versus girls, assuming that my probability of getting a boy as an offspring is 0.5? Right, instead of making all those calculations, like we did for the probability worksheet, we can find the probability of getting a boy first and then 2 girls, or a boy second and a girl first, and all of that. Right, we're going to kind of get to cut to the chase here and say, well, we'll just find it using the binomial distribution. Right, so our little p is 0.5, 3 children, that means our little n is 3. And if we want to show our probability distribution, if we are saying how many boys can you have out of 3 children, we have number boys. Well, we can have 0, we can have 1, we can have 2, or we can have 3. So frequency or our probability. We're going to read this off of our binomial distribution table. And here is my little n equals 3. Here's my 0, 1, 2, and 3 across my x-axis. My probability is 0.125. And 0.375. So for the 0 is 0.125. For 1, it's 0.375. For 2, 0.375. And for 3, it's 0.125. All right, so the binomial distribution allows us to, if we have a circumstance that fits it, that we can use this super shorthand for finding these probabilities rather than having to go through all the calculations. All right, so that's also how to use the binomial distribution table. You have to know your little p and your little n, so you need to be able to translate the question that's asking about this binomial setting into something that you can take and go to the binomial distribution table and find the answer to that question. All right, what is the next example for you? All right, so there's a couple of things that we could ask you to do using the binomial distribution. That's one of them, is go to the binomial distribution table, write down a distribution. All right, we can also ask to find population proportion and its standard deviation. Right, and this may be kind of the first part of doing a problem that has to do with binomial distribution, because we are going to have some situation where we have counts of individuals with certain characteristics out of a total sample size. And we want to estimate this proportion. We have these formulas to do standard deviation of our proportion. All right, so suppose we have some data that breast cancer rate in women in Ireland, age 60 to 65. Based on, we want to find this. We have a sample of 5,000. We found 50 women diagnosed. Right. So we want to find the breast cancer rate, right? That's the probability. And we have a sample of 5,000. So N is our sample size. How many did we look at? Our capital X is how many did we actually count up? Right. So we're just going to do our P hat, our estimated proportion is our X over our N. So that equals 5,000 over 500, which equals 0.01. Right. So that's my estimated cancer rate. right? I want to find the standard deviation for that because we always find that as well. And that's going to be this P times 1 minus P over N. And I found my P up here. I'm going to use my P hat. And then the square root of P hat times 1 minus P hat is 0.01 times 0.99. My little n is still my little n from up here, 5,000. And when I calculate that, it's 0.0014. Right. So that's not incredibly exciting or interesting. Right. Another thing you might want to do is find the mean and standard deviation of a binomial distribution. I did an example in the slideshow. Right, and we're going to use mu sub x, our mean of our binomial distribution. It's going to equal little n times p, and our standard deviation is going to be square root of little n times p minus p. All right, so we did the distribution, little n was 10 and little p was 0.2. Right, so we're going to do 10 times 2 equals 2, and we're going to do sigma sub x square root of 10 times 2 times 0.2, which is 1 minus p, which is 1.26. So those are some very simple kinds of calculations we could ask you to do relating to probabilities based on normal distribution. Interesting. Suppose we have a probability of recovering from Ebola. It's only 10%. And that's true in small children. If we have a ward in our hospital, which is a room that has 4 beds, we can find some different probabilities based on this scenario, right? What is the probability that all 4 children in a ward survive? Right, we can find out things like, what is the probability less than 2 patients in a ward survive? Right, so all these same kinds of probability questions that we were asking in our probability activity, we can translate into this binomial situation. All right, so I'm going to count recovery from Ebola as a success, not a failure. All right, and so I'm going to translate this into my little p equals 0.1. Now, in order for us to be in the binomial scenario, we have to have a sample of a set size that's fairly small. And in this case, we've got a situation that we're looking at a specific ward, a specific room. It has 4 patients in it. Now, this may seem a little bit contrived of a situation, but we might need to know this because of our hospital. We might need to know how many spaces that are going to be for patients in different wards. We may want to calculate some of these probabilities that have to do with managing and staffing our hospital. All right, so we're going to use this 4 beds in the ward as our sample size, little n equals 4. This is the hardest part of looking at a question you're being asked in your statistics class and figuring out how can I use either the normal distribution or the binomial distribution to solve this problem. Right, so you want to scrutinize the question you're being asked and see if it's something to do with a probability of success, and there's some kind of count of individuals that we're going to look at in order to evaluate that. All right, so what's the probability that all 4 children in a ward survive? Right, so we've got this 4 children, right, and we're looking at these 4 beds in the ward, or these patients, 4 patients in our ward. That's going to be our sample size for our binomial distribution in this case. All right, so this is the hard part. Once we've figured out that we are in the binomial situation and we go, aha, I have a little p equals 0.1 and a little n equals 4, then you are off to the races, right? What is the probability that all 4 children in the ward survive? Right, we can find that using our binomial distribution table, right? So once we see that we have a little p and an n, we are going to go to our binomial tables. The next quiz, some of you are going to look at a question like this. You're going to be completely stumped. You're going to have no idea what to do. And when we pass the quiz back and go over it and we say, all you have to do is go to the binomial distribution table, you'll do the forehead, hand to the forehead thing. Okay, so we're going to look at our binomial distribution table for our little p equals 0.1. So here we have our distribution. What's the probability that 0 out of 4 of our patients survive? That's 0.6. All right, this is a pretty deadly disease. This is scary. What's the probability that all 4 of our patients survive? 0. And it might not be 0, but it's going to have maybe some digits way out here. All right, so a smart thing to do once you have found the distribution in your binomial table, just go back to your paper where you are writing down your answers or you're showing your work, and you're going to say my little n equals 4, my little p equals 0.1. I'm going to write down my distribution. And this is my x and my probability of x. So 0 is 0.656, 1 is 0.292, 2 is 0.049, 3 is 0.004, and 4 is 0.000. Right, there could be some probability of survival that isn't 0, but it's out there in the many digits. All right. Now that I have my distribution written down, what is the probability that all 4 children in the ward survive? All right, I've got my successes here. Those are survival. What's the probability? That is 0. Out to the 3rd digit. Right. What's the probability that less than 2 patients in my ward survive? All right. The probability of x is less than 2. It's the same as the probability of x equals, let's see, less than 2, 1 added to the probability that x equals 0. Right, so the probability of less than 2 surviving, I'm going to take everything less than 2. It's an or question, so I'm going to add together. All right, so I'm going to take 292 and add 0.656. That equals 0.948. Not very likely. Sorry, very likely. Probability that less than 2 patients survive. for each ward for looking at them. All right, so in public health, we have a lot of use of the binomial distribution. And that's because in all of our public health scenarios, we are interested in what's the probability a patient is exposed to this disease? What's the probability a patient gets symptoms from this disease? What's the probability a patient is hospitalized? What's the probability the patient goes to the ICU? What's the probability the patient recovers? Right? And all of these things are either the patient recovered, the patient didn't recover, the patient was exposed, the patient wasn't exposed. Right? So incredibly powerful when we're looking at public health and different scenarios in disease epidemics and figuring out what's going on with them, what we can predict into the future, and all of that stuff we've been seeing examples of as the COVID pandemic has played out. All right, so let's look at an example where instead of looking at a single ward, which may be a little harder to understand why we might care about it. All right, let's look at our whole hospital. All right, so for a whole hospital that has 100 Ebola locations, our probability of recovery is still 0.1. Right. Now our n is 100, so we're not going to use the binomial distribution table. And we're going to change how we talk about question, because we're switching from a discrete distribution to a continuous distribution. We're going to have to use this normal approximation to our binomial distribution. All right, and the normal approximation is that we're going to find the mean and standard deviation of our binomial distribution, and we're going to use it as a normal distribution. It's that simple, right? Because our normal distribution is going to have the parameters mu and sigma. What we're going to do is we're going to take our binomial distribution, which has parameters sample size and probability. We're going to find the mean standard deviation of our binomial distribution, and we're going to pretend that it's a normal distribution with that mean and that standard deviation. And that's going to allow us to answer questions just like we were doing with normal distribution, using that mean and that sigma. So we're going to look at continuous questions across our x-axis. And in this case, we want to ask the question, what is the probability that more than 15 patients recover out of our whole hospital? So we've got 100, so we can ask these questions all the way from 0 to 100, but we aren't going to do it in this discrete where we have to add up the probabilities of each different discrete outcome. We're going to do it across this continuous axis. Right? So we're going to have a similar kind of question, but the way we're going to find the answer has a couple more steps. All right, so we've got our whole hospital is 100. Right, so we're out of hospitals with 100 patients. Our little n is 100. Our probability of recovery is still 0.1. So I have a binomial distribution with, 100, 1.1. I'm going to find my mu of x, my standard deviation of x. Right, so I'm in a binomial setting. but I need to use the normal approximation. How am I going to do that? I'm going to find the mean and standard deviation of my binomial distribution. I know that my equation from mu is ln times p. I got 0.1 times 100, that's 10. Sigma sub x is square root n times p times minus p, which is 10, because I did n times p up here. 1 minus p is 0.9. 3. So now I have normal distribution for my problem. If mu equals 10, and sigma equals 3. I'm going to find the probability that my x, my number of survivors out of my hospital, is greater than 15. Right? Where is 15 on here? 15, 16, 17, 18. Right, so it's not that far from my mean. So this is going to be my little x equals 15. And I want to find probability x is greater than 15. I'm going to go in that direction. I'm going to shade this in on my sketch. All right, so now I want to find the probability on using my normal distribution. And the way I do that is I'm going to have to convert these data from my data into standard normal table. The way that I do that is to convert to z. My equation is going to be z equals x minus mu over sigma. So that's going to be my x is 15, the value I'm interested in. My mu, I found it up here, it's 10. Sigma, I calculated it, it's 3. I've got 5 divided by 3, which is 1.67, should be a positive value. All right, now I'm going to go to my standard normal tables. And on the positive side, I've got my standard normal table here. Room for my standard normal table. My value of z is 1.67. I'm on the positive page, so I'm going to go to z equals, zoom down to 1.6. I'm going to go across to 0.7. That's 0.9525. All right, so remember what the standard normal table is showing me though. Right, and it's showing me at the top of this picture. This is the area to the left. Right, so my standard normal table is always going to tell me my area to the left. I've written down the probability, which is the area to the left. And that's not what I want. I want the area to the right. Okay, because that's what my question asked me. And I showed it on the sketch. Now I'm realizing that the sketch isn't a very good sketch, that I should have sketched it so that it was a smaller area here. Right, I showed this as a pretty big area. All right, so my probability z is less than 1.67 is 9.525. My probability that z is greater than 1.67 is 1 minus that, which is equal to 0.0475. Whew. Right, so my probability that more than 15 people survive out of my whole hospital of 100 people is less than 5%. It's pretty small. Right, Ebola is pretty scary disease. Right, so this kind of question All right, is just about the hardest kind. You're going to be asked to work this whole semester. There's a lot of steps. There's a lot of decisions you have to make, and realize what information you're taking from one step into the next. And we'll work some more practice problems of this in-person class on Friday if you need help with those. And then we're going to carry on and talk more about normal distribution, lecture, because use them to make inferences about things that we don't know. How can we figure out the relationship between the sample and the population? And it turns out that both the normal distribution and the binomial distribution are going to allow us to do that, to make a relationship, to calculate the relationship between the sample that we took and what is true in the population. So this is really powerful. This is a keystone of how we're going to be going about doing statistical testing for the whole rest of the semester. So hopefully you were able to follow along the logic of what we were doing today, but it's important that you spend a little time and do a little work understanding what these ideas are all about, so that you understand what we're doing as we keep going through the semester. All right, so the activities, worksheets, practice problems that we'll have for you are going to help you do that.